All right, thank you. So I'm happy to kick off, unintentionally, the faculty lecture series. I'm glad it's not snowing again. You know, I'll take the 50 degrees over the snow, I suppose. Just a reminder, two reminders. CS students who want credit for colloquium, make sure you sign up. And I'm the colloquium chair this year, so I'm allowed to do that. But yeah, it's up here, so don't forget, seriously, by the end. And just a reminder for next week, Jean Belviata will tell us about growing up internationally and how it shapes a child. Same time, same place. So I don't know anything about this, but I'm sure it's going to be great. All right? So I'm going to tell you a little bit about detecting and predicting home occupancy in a smart home. So before I can actually get to the occupancy part, I'm going to tell you a little bit about a smart home first. And why do we want a smart home in the first place? So energy use has consequences. This does not probably come as a surprise to anyone. And the society's energy demand has been rising over the past 20 years or so. It's expected to continue to increase over the next 20 years. And this is not just electricity, although that's what I'm going to talk about today. This is sort of energy use in general. And this obviously has lots of mostly bad side effects. Economically, everything's getting more expensive, right? Gasoline, electricity, and environmentally, there's all sorts of bad things that are happening. Pollution, oil spills, climate change, and sort of all that sort of stuff. And so hopefully I'm not going to spend too much time convincing you about that. That's usually accepted these days. But let's dive in a little bit and understand exactly how we're actually using this energy in the first place. Because before we can attempt to solve some of these problems and reduce our footprint, we have to actually understand what we're doing in the first place. So if you break energy use into two categories, you have sort of the generation side and then the consumption side. And one of the key problems and why this is an especially difficult challenge to really solve is that both generation and consumption is very fragmented. So if you look at the generation side, we're very dependent on fossil fuels, but not just a single type of fossil fuel. There's a lot of them, and we use a lot of them, and they're a finite quantity that we are depleting, which is also a problem. And the good news is there are some alternatives that are renewable, solar and wind, and we are beginning to rely on them more and more, but we're still only at about 17%, and although there are incentives to continue to increase, we're not going to break over and start using more alternatives anytime in the near future. We're still going to be very reliant on fossil fuels for at least the next couple decades. So then flip to the consumption side, and if you break consumption into three categories, so buildings, which are both residential and commercial, industry, which is basically everything from data centers to factories, and then transportation, planes, trains, automobiles, that's also pretty fragmented. So buildings are a bigger fraction, using about half, but then the other half is split pretty evenly among these other two categories. So why is this fragmentation a problem? Well, because there's no target, right? There's not sort of one solution that's going to solve all of our energy use problems and make this all go away, right? So with all this fragmentation, it's not clear what we should actually do about it, right? So we have to start picking at little pieces. So I'm going to pick one little piece. I'm going to focus in on that 48% building usage and see if we can dive into that a bit more. And in particular, I'm going to look not at energy use in general, but just at electricity. Okay, so if we look just at the electricity use in buildings, we can actually see that there is a bit of a target now, okay? So electricity in general is important. It's about 40% of all US energy generation, and in general, clean energy tends to be electric. So if we can increase our dependency on electricity, that's actually not a bad thing moving forward. Within that, if we look at buildings are the dominant load with respect to electricity consumption. So 76% of our electricity goes to buildings. And just as a side note, because I didn't find this obvious, if electric vehicles actually become really popular, that will increase the building load, right, the building percentage, not the transportation percentage, because our buildings have to be outfitted with the plugs that actually charge the electric vehicles, right? So it's not going to shift it towards transportation, but rather it's actually going to increase that percentage even more. And so the idea then, and sort of the motivation behind the bigger research project that I've been working on, is if we could focus on this 76%, and if we could make our buildings smarter by making them greener, right, we could actually reduce this consumption and at least start to chip away at the bigger problem of how we can become a more energy efficient society. So how do we then make buildings more efficient? All right, so the high-level goals are we should reduce waste, cost, and environmental impact. It's sort of summarizing everything we could want to do. So how do we go about doing this? Well, the obvious answer is we should just use less electricity, right? If we all stop using electricity, we would consume less and the problem will be solved, all right? So the problem with this is if we expect humans to do it manually, right? We call this the manual approach. This is Little Miss Stubborn, I believe, I hope. That was who I was hoping that was. If we leave it up to occupants of homes and buildings to basically decide when they should turn things off, it's not very effective. And even if it's effective in the short term, people are they're creatures of habit. They're not going to make long-lasting changes to their routines. So we're not going to have a huge impact sort of in the long term in actually solving these problems. And the other problem is people just don't care, right? So in the words of the Lorax, unless someone like you cares a whole awful lot, nothing's going to get better. It's not. And so there aren't enough people who actually care to make a difference to really rely on just people changing their behaviors to solve the problem. So what we'd like to do is actually do something more automated, okay? And that is make our homes and our buildings smarter, right? Let them decide, let the houses and the structures we're living in actually decide when it's okay to turn things off and on so they can try to make better decisions about the way we use electricity, and energy in general, but especially electricity. And in some ways, buildings are in a better position to make the decision anyway because they can look at a bigger picture. They can collect data from all over the building, they can look at historical data, and they can have a computer that's actually solving some of these hard problems that it's hard to make as a human in one sort of piece of the building. So this is not, this is kind of a hot area right now. Some of you may recognize the Nest thermostat. Google just acquired Nest for some ridiculous amount of money. So Google's soon going to know all about your thermostats and your, how hot or cold you like your house. But what the Nest thermostat does, if you aren't familiar with it, is it tries to figure out, using some computer science algorithms actually, machine learning, it tries to learn over time when you're home and when you're not home, so that it tries to basically preheat and pre-cool your home appropriately in a more intelligent way than just using a programmable thermostat. Because I don't know the number and I should have looked it up, but there's some really ridiculous percentage of people who have programmable thermostats and don't know how to use them correctly. And so actually, as a result, they actually use more energy. It's actually like counterproductive to use a programmable thermostat, and I know at least one family, my in-laws, are really guilty of that. They live in Alabama, and if you visit them in the summer, you should take a coat. And if you visit them in the winter, you better bundle, because it's like, bring a t-shirt, because they just think that it should be extremely opposite of what the outdoor temperature is. And they don't know how to work it, so they just like basically set it to really high temperatures and low temperatures, and they aren't alone, okay? So the point is programmable thermostats aren't enough. They need to be something more automated and something more intelligent. So what does it take to actually build a smart building or a smart home? So I kind of broke it into two categories here. There's the sort of the technical, the actual infrastructure building half, the top half, which is I'm calling data collection and control. So how do we actually build something that is going to, this infrastructure that both collects data, because we need to know what we're actually using before we can make any decisions about what we should turn off and on. And then how do we scale this so as homes get bigger? How do we continue to make this infrastructure actually work? And then how do we actually control devices, right? Because if we're expecting our house to turn things off and on for us, they have to have that ability, right? How are they actually going to do that? So that's sort of the first half. And then the second half is all of the somewhat maybe more tricky algorithmic and policy issues. So once you have this data and you know how to turn something off and on, and you're collecting data about how much energy you're using at any point in time, when do you actually make the decision, right? How do you actually know it's okay to turn something off? And that's a much harder problem in some ways because there's a lot more, you have to take sort of occupant preferences and things like that into account. And this little picture over here I'm not going to go into. I actually talked a little bit about this at my Sigma's iTalks, a year and a half ago or so. But one thing we've looked at is how you can actually schedule certain devices. So if you just take things like air conditioners and you run them all at the same time, you're using a lot of power all at once. But if you can just somehow flatten them out and use them serially rather than all at the same time, you're not using less energy overall, but you're reducing the peak, and that's a really good thing if you're maintaining the power grid, for example. And so I'm not going to talk about that today, but that is something we've looked at. And those are the types of things you can start to think about when you're talking about building a smart home. When should you turn things off and on, and how do you make these optimal decisions? So we've been looking at this. I started this project when I was on my AP leave a few years ago. So this is with a bunch of people at UMass. And it's the project we call the Smart Star Project. The goal of the project was basically to build a couple of these smart homes, we call them our prototypes, and then see if we could actually come up with a good system for collecting it and collecting the data, figuring out how to control devices, and then once we have that data, then we can actually start to look at some of the harder questions, the algorithms and the policies. So the focus on this project, rather than some of the other projects, is breadth, though. What we want to do is see if we can get as much data as possible out of a home. Right? How much data can we actually collect from lots of different sources, uses lots of different sensors, and we didn't want to have to build anything ourselves. Okay, so we wanted to use off-the-shelf components that you could just go buy for almost all of them are less than $100. Most of them are much cheaper than that. And we just wanted to kind of glom together a bunch of these things and see what all we could get working together in some sort of reasonable way. We've been doing this now for about 3.5 years, so we have lots of data and seasonal changes, which is kind of cool. So you can see how the weather actually impacts your energy use. And then there's a lot of redundancy, so we're collecting sort of readings from the same source in different ways so we can error check, because our data is never perfect, but at least we have some amount of reliability built in to know if we're accurate or not. So just some basic statistics about it. We've done this in 3 houses in the sort of western Massachusetts area. One is mine, and that's the one I'm going to talk about today. We have over 100 distinct sensors running, doing various things, and I'm going to talk about that at all different levels. And the time granularity is usually down to about 1 reading per second, sometimes finer, but that's sort of the average overall. So lots of measurements happening. Okay. We also have a microgrid data set that is actually 400 houses spread across the US that we are also collecting their aggregate power usage for, which is kind of cool because now we can get more information about different parts of the country and different regions, but those homes are not nearly as fully instrumented as ours, so we can't do quite as much with that yet. But we are making all of this stuff publicly available because our goal is not only to enable our own research, but we're hoping that other people out there who want to explore some of these things can leverage the work that we've done. But for the remainder of my talk, I'm going to focus on that top one, the home data set, which is my house, and tell you the crazy things we've done to our house. All right, starting with our electric panel, okay? So, yeah. We talked about either doing an addition or moving because we need more space, and then we realized if we moved, we'd have to uninstall it, and that was a big decision to not move. We're a little afraid if anyone walks in the house and sees that, what they're actually going to make us do to it. But anyway, so what all of these crazy things are doing is actually measuring the aggregate power usage in our house at any point in time. So it's going to measure both the real and apparent power, if you know what that means. If not, not important. Pretty accurate, and at a 1-second granularity. And if you look, there's sort of a couple pieces to it. There's the thing down the bottom here, this is called the E-gauge device, and an alternative is a TED device. Some of you may have heard of it. This is much more accurate than TED. If you're interested in doing this to your own home, talk to me. I can give you some suggestions. We've tried both. This thing is basically kind of like a little mini computer, but instead of talking on the regular Ethernet network, it actually speaks on the power line. So it sends messages using the electric lines in their house rather than the Ethernet, and we just have to convert between the two. But it just sits there and basically gathers data. There's 2 CTs that are bigger that sit up top, and they're coming in on the 2 different phases on the house. There's one on both the right and the left side. And then there's a bunch of these little CTs that are on each individual, circuit, okay? And that's measuring the circuit level data. All right, so we have the overall house aggregate power coming in, and we also have each individual circuit using these little CTs that are measuring it. And again, the granularity is every second. So we're getting the real and apparent power on the 1-second intervals. The nice thing about this is a lot of the big power-hungry devices in our house, appliances, actually are single device circuits. So things like your refrigerator, your dryer, microwave, in many cases are going to be on their own circuit. So just doing this actually gives you enough information to know what that appliance is doing. That's not always true, but for many of them, especially things like the dryer, which are really big power users, if it's an electric dryer, this gives you enough information to actually say something more detailed. So what this thing does is it collects all this information and through a bunch of translation I won't go into, essentially posts it to a web page. If I can figure out how to, there it is. Okay, so that's currently my house in real time, how much power we're using. And you can see, without going into it too much, you can also click down and see what individual circuits are doing. So right now we're just looking at the aggregate usage. You can see we have some funny stuff that runs every 20 minutes every hour in our house, and some other weird things that happen. And it just went off, right? So if this is looking at, if I go back to the last hour rather than 10 minutes, I think you'll see that spike lasts for about 20 minutes. Yeah, and then goes off. All right, so we have a HRV, a heat recovery ventilator. It's an air recirculator that runs in our basement for 20 minutes every hour because our house has spray foam insulation and the building inspector made us do it. Okay, but it basically just pumps air in from outside to keep it from getting stale in the house, more or less. And in the winter, it heats that air, which is why it's electric heat. It's very inefficient. But if you don't do it, you're literally, throwing 30-degree temperature right into your house, and it's right in our living room, so it's kind of not ideal. But that's what that spike is. All right. Okay, so in addition to what the E-gauge gives us, and the E-gauge is pretty cool, I mean, that gives us a lot. We also measure individual outlets, all right? So there's two ways we do that. One is using this thing here, which is Insteon is the protocol. It's called the iMeter Solo. It literally just plugs in. This is my hand to give you a scale for how big it is, and you plug this into the wall, and then your device plugs into the bottom. And that speaks two protocols, which is nice. One is the power line again. It speaks Insteon over the power line. And then another, it also speaks a wireless protocol. So that way you can get the same message twice, but it's more reliable that way. The limitation is it's a little bit less. We can only get one reading per second across all devices because of the way it does its communication on the power line. So this can be a limitation if you have a device that is kind of turning off and on very frequently. You might miss a little bit of data, but it usually doesn't happen. In addition to these, we have these other outlet meters installed. They speak a protocol called Z-Wave, Zigbee, if anyone is familiar with these things. A little bit more expensive, only wireless. They don't speak power line, which is kind of a limitation, but they're faster. So we can actually get these readings once every 50 milliseconds, which is a lot better. The downside of these is since they're only wireless, and you plug them into an appliance that is not always in an optimal place in your house, it's hard to actually get the reading. So like our refrigerator, for example, is kind of tucked in a little nook, and you can't really use this, even though we want it to get the power readings from that. So there is some limitation there. All right, so to summarize, we have these things plugged in. So in addition to our circuit data that we're collecting and that's printing over there, we're also getting over 90% of the plug loads in our house. One issue moving forward is if you look at a bigger home, I don't know how well these things are going to scale. And that's one thing we've talked about. It works well in our house, which is only about 1,700 square feet. But it's not clear if you keep doing this when that's going to become a bottleneck and when we're going to have to think of something a little bit more creative. In addition, we swapped out all of our light switches with these things. That's, again, my hand to give you some scale. So these are also speaking the same protocol as the outlets, Insteon. Just sends a message every time a light is turned on or off, as well as the dim level. So we have all dimmable lights in the house. And then this gives us the ability to correlate circuit data with actual switch events, so we know when stuff is happening. Other stuff that we keep track of, motion. We have a few motion detectors, which aren't as useful if you have a pet, right? You might think that a motion detector is really good for occupancy detection, but if you have a dog, fortunately my dog doesn't move very much, but yeah, it's not. In fact, I'm more alarmed when she does move. I wonder what's going on than when she's not moving. But we also we don't actually keep the external door. We have a door sensor on our refrigerator and our freezer, and for a while the data was really wacky because we found out that my 3-year-old was carrying around the little magnetic device. And so, we were getting data that said our refrigerator had been open for like 45 minutes, and that was not true. They're now duct taped, and at least so far he hasn't solved that problem. And our furnace, or our thermostat, also speaks Insteon, so we know when it goes off and on if we change it. We were also collecting GPS from Google Latitude for the adult occupants in the house. Google Latitude was discontinued in August, 2 days before my daughter was born, and I have not yet hacked up an alternative. I think Google Plus will do it, I just haven't gotten around to doing it yet. We keep weather data, so we have a weather station, 1-minute granularity. We're sucking all that data in as well, so we can correlate that with our energy usage. And not at my house, but at one of the other houses, we're also doing some solar panel and wind turbine generation. We're not using the energy, actually, at this point. We're just measuring it, but we're working on expanding that a little bit more. So we have all these weird devices. How do we get them all together? So this is kind of an architectural diagram. You can see the switch events and the different appliances. All that data has to somehow get collected. We call that the controller. What the controller is in our house is this tiny little thing. That's actually a whole computer. It's about the size of 2 decks of cards stacked together that just plugs into the wall, has a bunch of USB ports, and we use that to basically suck the data in. And then I think twice a day, we take that and shove it out to an actual server that is a little bit more reliable. So that's where we actually do all the data collection in the house. All right. So to summarize everything I've just said, this is all the data we have to work with. Right? We're using this Insteon protocol for the, I'm not going to go into the details about how we actually convert from the power line, but we're grabbing all the information off of our switches and our outlets combined with the Z-Wave to do some of the outlets, and then lastly the E-gauge to give us the aggregate power, and then our weather and GPS coming in from the weather station and what used to be Google Latitude. Okay? So that's the collection side. Tell you really quick a little bit about the controlling side, and then I'll actually get to the occupancy stuff that I wanted to tell you about. So the Insteon and Z-Wave protocols allow us to have very simple device control. And I say simple because basically the only thing they do is they can disable the power on the circuit or on the outlet, right? So if your device is simple and basically only has two states, on or off, this is fine. This will not work for some more complex devices. But I was going to show you quickly, since you're seeing maybe it needs to be refreshed. I could actually show you what happens if I turn the lights on in the house. Let me see if I can get it to behave. All right, so I'll turn the living room lights on, and you should see here I was testing that it worked. I don't know, the network is not refreshing it how it should. Let's try 10 minutes and see if we get that. Okay, let's try this. So unless I've lost my connection, in which case I can't actually show you. All right, so right now everything's off. If I turn the lights in the living room on, other than potentially waking up my sleeping dog, we should see a jump slowly. All right. I like to do this demo using a dryer, but it turns out I have to actually be home to put, I don't know, I'm a little nervous about running the dryer with nothing in it when I'm not home. I don't know. But the dryer uses a lot of power, so it's a little bit more exciting. And then if we can dim it, so we might be able to see that should drop it down to 75. So if it ever catches up, you'll see sort of the stair-step thing happening here. Dropping it down to 50%, and then 25, so you can get the... So this is just showing you, all I'm doing are turning lights on and off. So if it's a simple device, right, this works well. This does not work for more complicated. But you can also see our interface needs a lot of help. So I'm literally typing these random things, which means a lot to me, but wouldn't mean a lot to most other people. So we haven't focused on the usability side of this at all. It's just proof of concept. We can do it. All right. I guess we'll leave the lights on. Wake my dog up for a little while. All right. So how do we do more sophisticated control? So fortunately, some manufacturers are now actually starting to embed this capability into the devices themselves. I also really would like someone to try to hack a coffee pot this summer. I'm trying to get a summer student who wants to see if we can take a coffee pot apart and plug a little Arduino programming board into it and see if we can actually do some more sophisticated control. I don't know why I'm picking a coffee pot. I feel like that one's there's less chance of burning something down if it's just a coffee pot. To see if we can do some of these more complex control mechanisms on something that's not meant to have it, basically. But we do have a Wi-Fi enabled washer and dryer, which we haven't really done much with, other than we thought it might be cool to play with this. It's not very open in the sense that they don't want you to hack in and see what it's doing. So we've tried, we haven't made progress yet, but we're going to come back to that. But it really would be much more cool if there was a robot that would move things from the washer to the dryer, all right? But we do have, this is what the interface looks like on the iPhone. I mean, you can literally it's very simple. So we feel like there's got to be a way to plug in and actually do some control. We just haven't, the protocol's closed source and we haven't hacked it yet. All right, so lots of data, right? Lots of devices. We collect over 5 million points a day, so now what? So we've done lots of sort of cool things with it. Today I'm going to focus on a problem that students have mostly worked on here with me, and that is detecting and predicting occupancy. So our previous goal back early on was, I said we wanted to make the house smart enough to turn things off, right? And we want to do it in a way that it doesn't bother the occupants, right? Because people don't want to be bothered. They don't want to be inconvenienced. So we want the house to be smart enough to do this in a way that essentially the occupants don't even notice, okay? And so part of doing that includes being able to figure out when people are home or not, right? So the occupancy detection, although it may not be the only way to go about doing it, certainly it simplifies the process. Because as soon as you determine that the house is unoccupied, then any interactive device, and interactive are things that you basically control, right? You walk over and turn the switch to turn them on. TVs, microwaves, toasters, etc. If they're left on and you're not home, you can probably safely turn them off without bothering anyone, okay? There's a few weird cases here, like a dryer, right? You may turn a dryer on and leave, so that's one that we're not really sure if that should count as interactive or not. It's interactive in the sense that you have to be there to turn it on, but not necessarily for the duration of its cycle. So that one's kind of a weird one. The prediction side is used mostly, the thermostat is the best example of why that's needed, all right? So if you can preheat or pre-cool your home based on, if I know you're going to be home at 5 o'clock, then I'm going to go ahead and set my, make sure your thermostat is fired up and, the house is nice, toasty, whatever, 70 degrees when you walk in the door, All right, that's the best application for the prediction as of right now. All right, so let's talk about the detection first. So it's easy to detect the occupancy if you have a house like ours, right? We have the circuit level data, the outlet level data, and if we know all of that, then it's pretty easy to figure out when it's okay to turn things off, right? If we know that interactive devices are being used, that probably means we're home. If interactive devices are not being used, it probably means we're not home. And there's a couple weird edge cases you have to consider, but for the most part, it's not too bad to figure that out. There's no way you can expect all smart homes or all homes to be fully instrumented like this, though. Right? So what we were trying to do is take our smart home and the data we've collected in our home and find a model that we could then apply to less smart homes, right? And so we might need a little bit of information, right? They might not be able to be sort of your standard house with absolutely no data collection going on, but maybe just knowing the aggregate power, for example, if you had that much information, is that enough to actually figure out when you're home and not, okay? So the first approach, which is or sort of what your intuition may be telling you, is that you should just look at sort of the average, right? You're seeing this spike and sort of do some averaging and some smoothing and just try to find a threshold, right? And so find some threshold that says if you're using more than this power, you're home. If you're using less, you're not. And hopefully just seeing what's happening right now as I'm talking, you can realize that that's actually not going to be very accurate, right? And so the problem is that although it's fast and easy to compute this, you just literally say how much power am I currently using? Is that bigger than my threshold? Yes, then I'm home. Otherwise, no, I'm not home. It's hard to do, right? There are periodic devices that run in your house, some of which use a lot of power, and they will throw off the ability to find this average. There's also issues with day versus night, right? Chances are you're not doing a lot of interactive stuff at night, or maybe you are. In my house, we are up all night, many nights, so, But in a normal person's house, you probably would not be up all night. Weekend versus weekday. Weekends are very hard to predict because people have varying schedules on the weekends, although weekdays tend to be a little bit better. Summer versus winter. Our house has gas heat, but we use sort of window electric AC units, so there's going to be a difference there. And so trying to come up with some threshold that just always works is very hard. So next, and this is stuff that Sarah Abramson and Kelsey Levine worked on this past summer, the intuition was, okay, well, humans are creatures of habit, right? So maybe we do something a little bit more creative than this threshold thing, but let's just take some period of time, let's just build like an oracle, right? Let's build a database that looks at our usage over some window, right? Some, a month, 2 months, whatever, and let's keep track of the day of the week, the time of day, how much power we're using, and then let's actually use the circuit level data in the house to figure out if we were home or not. All right? So we're going to build this database of basically just days and how much power we're using on those given days and what time of day it was and things like that. Then for the current day, right, say, well, how much am I currently using, what day of the week it is, and what time is it, and go into that database and see if you can find n closest matches. And it turns out n doesn't really matter that much as long as it's sort of more than 5 and some reasonable number. Right? But you're looking for days that look a lot like the current day. And then if you use that to help, then maybe you average it or you do something creative with looking at if you have sort of half the time you were home and half you weren't, right? Look for the days that are the closest and then use some sort of average to figure out with some level of confidence, I'm going to guess that you are currently home, right? You're using this much power. The last 10 times you were using this much power on this day, you were home. I'm going to guess that you were home again. And that doesn't need any circuit level information, right? We're only going to use the aggregate level information at that point. And so it turns out doing this, we actually got pretty high levels of accuracy. So we around 85% in the best case, or sort of on average, and then more in some cases. This worked pretty well. The downside is it's not clear, and we haven't tried to figure this out yet, how well this actually would help other homes. Right? Is knowing exactly what we do in my house at all helpful for someone else? I don't know. Right? And maybe the model, maybe the rough model will work, but we need to extend it or generalize it in some way. But this is where we're stuck right now, is how do we go from here to another house? Does it help at all knowing what we did? And so just kind of a cool picture that Sarah made this summer. The thing at the top is actually what her algorithm was detecting. Right? And so what you see here is just, I believe it's, what is it? It's from 6 a.m. to 11 p.m. on a given day. The red line is the aggregate power usage. Those parts that are shaded in blue are where her algorithm said that we were home. The parts that's shaded in orange that isn't showing up very well in the middle is if you look at just the circuit level data, when would we say that you were home? And this, which we consider the ground truth, is what our GPS coordinates on our phones were saying. Right? And so what's interesting is there's some weird cases where even the circuit level data isn't good enough, okay? Like right here, what probably happened is I dropped the kids off at daycare and came home using a laptop that wasn't plugged into the wall for about an hour before I then left again, right? Or however long that was, a half hour. And so I never did anything. So there was no way for the house to actually know that I was home because I just walked in, sat down, didn't turn on a light, right? But I was actually there. So that's tricky, right? This is why this problem becomes a little bit, it's not as easy as you think it might be at first glance. But you can see that her algorithms did a pretty good job, right? There's a few weird cases. Nighttime is a problem, right? Because we're not doing anything. But for the most part, her algorithm, with a few kind of weird exceptions in the middle of the day, was able to correctly guess when we were home and when we weren't, if we assume that this GPS is actually the ground truth. Okay? All right, so the third approach we tried, and this was Jennifer Gosselis did this for her thesis last year, was a little bit more complicated and actually tried to solve a harder problem to get at this occupancy detection bit. And what she was saying is, all right, we know that interactive devices indicate occupancy in most cases. So if we can take an aggregate power curve, disaggregate it, so we go from the aggregate power and actually can figure out exactly which appliances are running, just based on like the signature of the curve at that point in time. Once we know the appliances, well then we can make some assumptions about whether or not you were home or not. But this disaggregation step is actually really hard, right? So she was trying to solve the harder problem just to get back at this occupancy detection. And so what she did is actually use some machine learning algorithms and the circuit level data to try to learn what patterns do you frequently see. So she was literally looking for patterns of or groups of appliances that you frequently see together, right? So maybe you always see the coffee pot and the toaster and the kitchen lights run at the same time. So she wasn't just looking for individual appliance signatures, but rather sort of groups of appliances that often run together and make this sort of same looking shape in your aggregate power curve, all right? And so the same way there, she had to use circuit level information to learn, right? We called this the clustering step, but then you could take, once you have built that, you can then just use the aggregate power information to actually use those models to figure out what's happening without the circuit level information, using only the aggregate power curve. All right, and she did pretty well too, so we had over 87% accuracy using this technique, but this was pretty expensive. I mean, just running these algorithms over the data actually takes a little while. And this problem of disaggregation is, like I said, I think that's actually harder than just detection in itself. So this is an interesting problem, right, just by itself, trying to do this disaggregation. But if the goal is only occupancy detection, we may not need to actually solve that hard problem to get there. All right, so that's kind of where we are on the detection bit. On the prediction side, right, we kind of used the same idea as we were using for Sarah's approach on the detection, and we said, well, let's look at where we are right now. So if we break our day, the current day, up into 15-minute segments, and we basically are going to say, put a 1 in a little vector, a one-dimensional vector or array, that says that we were home for that 15-minute window, and a 0 if we weren't. And so we're going to just keep track of that for the current day. And then at any point in time, if I want to predict what the rest of the day is going to look like, I take the current day's patterns of 1s and 0s, go look at all the previous days that I've kept track of, and figure out, does this day look like any other day that we've previously seen? And it turns out if you have, if both adult occupants in our house work and we keep fairly routine schedules, you do see a pretty good pattern emerge. Weekends are harder, right? But for the most part, Monday, Wednesday, Fridays look a lot alike, and Tuesday, Thursdays look a lot alike, okay? And so using this is basically what this vector was going to look like. You just split your day up into 15-minute chunks. As soon as you leave, you start inserting 0s. When you're home, you use 1s. And then when you come home again, you would start inserting 0s. Or sorry, start inserting 1s again. And so using this, we can then see how well we can predict what the rest of the day is going to look like, which would be helpful for, again, the preheating and the pre-cooling stuff. All right, so lots of numbers. The only things you really need to look at are the ones down here that are shaded in yellow. But basically, we tried this with 2 sets of data. One was using the GPS as our oracle, right? Using the GPS to learn based on the GPS data. And then the other one was using just the circuit level data again. And you can see that, not surprisingly, as the day progresses, we get more accurate, because the more information we have to work with, the better we can pick matches in our database, right? So that's not too surprising. And in the best case, when we're at around 5:30 p.m., if you're trying to predict the rest of the day, you can see 88% accuracy or so when we're using the GPS, and 93% when we're using the circuit level, okay? It gets worse again because there's so few spots to predict that even one wrong answer jumps knocks down the percentage, okay? So hopefully at least some of you are thinking, well, this is kind of cool, but also kind of freaky, right? So if we can detect occupancy using just power in your house, so can utility companies, and so can anyone who hacks your smart meter or your Nest thermostat or anything like that, okay? So now that I told you how you could detect occupancy, what can you do to make it such that you cannot detect occupancy, all right? So what do you have to do in your house such that this is no longer possible, okay? And so the intuition is we should just eliminate these detectable patterns, right? So everything is kind of based on this pattern matching thing. And so if we just get rid of these patterns, then, you know, we don't have to worry about it anymore. So the really dumb, energy inefficient way to do this is just always use the absolute. So pick the maximum you ever use, which is probably when you're running your dryer, all right? And always use that much power. And so we did this. Okay, this is my husband, and he made me promise I wouldn't use this picture, but then I did it anyway because he was running this experiment. There's a good story. He was running this experiment when he was not supposed to be, and I got a panicked phone call one day last spring saying, I've lost connectivity to the 30 light bulbs in the basement, and they're all on right now. Go home and turn them off before they catch fire. So basically what this little silly setup is it's literally 30 100-watt light bulbs that try to figure out how much power we're currently using and then turns on enough light bulbs to make sure we always are using a flat, 5 kilowatts or whatever it is, right? So about as wasteful as you could possibly imagine. We weren't really seriously going to do this. We were mostly just proving that we could actually implement this on our system. But yeah, he literally was testing this one day, and the rule was he was only supposed to test this when we were home. And he was testing it one day when we were not home, and yeah, he got a panicked phone call saying, all 30 light bulbs are currently on full power, and I can't turn them off. So that was bad. This is no longer functioning in our house, all right? So, but this is silly, but can we build on this idea, right? What can we do? So one idea is to use what we call what's called BLH, battery-based load hiding. And so the idea is if you have some renewable energy sources that are actually charging a battery in your house, you can kind of do the same thing we were just talking about, but rather than trying to use the maximum amount of power at all times, just use some constant amount of power, right? It doesn't have to be your max. So the grid, the electric grid, is only ever going to see this amount T. And then everything that goes above that, you would use your battery to charge that, all right? That seems promising, and it actually works reasonably well, but battery technology isn't ready for this yet. Basically, batteries are too expensive, and they don't quite have the capacity needed to handle the maximum load that most homes are going to use, right? So this was sort of the first step. Doesn't work very well unless you don't use much power. So then we said, well, where are other places in the house that we could kind of take advantage of this extra energy, right? How can we achieve this without just wasting energy with light bulbs? So the idea was thermal energy storage. So space heaters or, hot water heaters that are electric, right? We can use the energy that would already be used to heat our water, and just if we do it in a creative way, we can actually still, right, expose to the grid some constant amount of power, but rather than just wasting that electricity for the light bulbs, at least we're doing something useful with it, right? We're heating water. And so this was a little better. It still wastes energy though, right? Because maybe we don't need the water to be heated at this time, right? So, we're not just literally lighting light bulbs, but we're still not saving any energy, okay? We're still wasting energy. So then we thought, okay, well, what if we do just random stuff, all right? So if the fact that our curbs follow these very specific patterns is the problem, let's just make them look let's just inject noise, right? But we're going to make it realistic noise. So the idea is we want it to look like we're always home, for example, okay? So we kind of we look at some of the common patterns, and then we would just artificially inject noise by either turning on a light bulb, or we could use the water heater. It doesn't really matter where it's coming from, right? But we're going to expose to the grid the normal amount of power plus some little extra stuff to make it hard to actually predict when we're home and when we're not, okay? This works reasonably well and is probably the most efficient, at least that I've said so far, in terms of wasting energy. But this still doesn't hide as well as a flat line, right? This still gives you some ability. It's harder. You've made it more difficult to detect occupancy, but it's still possible. So the sort of hybrid that seems to work the best overall is this approach that actually combines the flattening with the artificial signatures. And so the idea here is we'll flatten to some point. It's not going to be the peak, right? We're still going to use the water heater, the thermal energy thing, to offset some of that, and we are still going to inject these random power signatures. And although this picture doesn't reflect it, what's kind of cool here is you can actually schedule things differently, so you're not really wasting any energy, right? So this is sort of showing you just for proof of concept how you might do this, but I could just as easily just run the water heater at slightly different times than what I would have normally. So you can make it such that you really aren't wasting that much energy at all, okay? And so this works well if you actually do have some sort of electric water heater. We don't, so we were using another data set to do this simulation. But this is kind of where we are with this. And if you do this, you can reduce the possibility of being detected by about 10 times, right? So you can really reduce the effectiveness of our occupancy detection algorithms using this trick. All right, so to wrap up, some of the other things, I've talked about these top two basically a little bit today, how we actually do the scalable load monitoring and how we do this non-intrusive load monitoring, which is the disaggregation stuff. If you came to my Sigma Xi, I also talked a little bit about the demand flattening, but this is something cool we've done where if you can just shift the way you use devices around rather than trying to always deactivate to save power, you're not reducing your total energy consumed, but you're reducing the peak, which is good for the grid, and especially if like entire neighborhoods start doing these sorts of things, there's a lot of potential to reduce the costs to maintain the grid and use cleaner energy sources for energy or for electricity generation. We're also looking at renewable sources. We have not done much beyond what I've told you today with batteries. Like how do batteries kind of work into all of this? And when should you use a battery? So the question is, if you did have a battery, when should you charge it? When should you drain it? How does this sort of factor into the whole equation? And that's one thing we're looking at moving forward. And kind of related to that is electric vehicles, right? They have a battery that's just sitting there if you're not driving. And so can you actually leverage the battery in an electric vehicle in a way that you can kind of use the capacity of the battery, but also make sure that that battery is charged when you actually want to drive the car? So it will be kind of combining your whole occupancy, detection, prediction, when are you going to leave the house sort of thing, kind of a big merging of a lot of these ideas. And that's sort of, we don't really even know how to get started on that right now, but that's sort of in the direction we're thinking about. So some acknowledgements. Sean Barker is actually Williams. He was my first thesis student here, but he's at UMass now. He's one of the main students working on it, as well as some of these other guys over at UMass. Students here, Sarah, who did the occupancy detection and prediction this past summer. Carlin was doing an Android app a few years ago that basically plugged into the eGauge thing over here to help do some very rudimentary monitoring and control. Jennifer Gossel's thesis last year looked at the detection and prediction, and Kelsey Levine was basically made a cool iPad app that displays this in a much more user-friendly way, and she's also was helping Sarah with some of the occupancy and detection stuff. Okay, so to summarize, building sustainability is an important and rapidly growing area. People are very interested and excited about this because it's something that we all need to start thinking about a little bit harder for our future. Smart homes and buildings are one possible way we can start improving energy efficiency, and this is especially going to be helpful if we can do it without bothering the occupants, right? If occupants were willing to change their behavior a little bit, it gives us many more options, but that's sort of outside of my expertise, right? How do you actually make people listen, okay? Smart buildings need to be able to detect and predict occupancy to help make some of these optimal decisions. So I've talked about some of these models for detection and prediction. Where we are, as I said, is we'd like to know how these models, if they can be extended, such that the stuff we have found for our house and our data can actually be used on other homes with less instrumentation. Basically, is there any use in doing all of this on our house that can it be more broadly used? And of course, privacy is a concern, and that's going to continue to be a concern as these Nest thermostats become, connected to Google Plus and people start hacking them. There's sort of a lot of scary things that could come about as a result. All right, so with that, I'll take questions.
So why is it bad if you mispredict you being home when you don't use any appliances? Like, it seems like it'd be okay for the house to think that you're not home.
It may, from a smart home standpoint, that may be totally okay. It's just from I wanted to get 99% accuracy in my data collection. But yes, there's the good point that if you're not actually doing anything, the house doesn't care, right? The house only cares if you're actually doing something.
So what kind of ways might you move towards better metrics for measuring like the utility cost for it mispredicting you being home or not?
Yeah, I don't know, actually. I mean, this is, evaluating the accuracy of this has already been a challenge because we do all this stuff and it's like, well, all we have is the data that we've collected for the past days. And so that's when we started using GPS. It turns out GPS is sometimes not reliable, so that's not a perfect, perfect solution either. But I think the metric, it all depends on what you're trying to optimize for, right? So if you're really trying to reduce electricity, then I guess your electricity usage would be the metric that you care about. But if it's sort of, comfort, right? I don't know how you measure these sorts of things. That's some other department on campus. So I don't know. It's a question that we've been struggling with, and we don't really have a good answer for it yet. But it's important, right? We need to know how to know if what we're doing is actually useful. Yeah?
Yeah, I like your talk a lot, Jeannie. I'm curious why you don't use motion sensors in your house. If you put like a motion sensor in certain areas of the house, like maybe in front of certain appliances or over a sofa, or places where you're likely to sit or something, it seems like you get more accurate than a GPS, and you'd be able to figure out patterns based on where you are and what you're doing.
We do have motion sensors, and we have that data. They are somewhat unreliable because the ones we have, and they may have better ones, they don't give you like a spectrum, right? I mean, I guess, I don't know if you saw it on the ceiling or something. So basically, you have to kind of walk in its little eyeball, right? And so if you're shorter than that, it doesn't catch it. If you happen to walk around it in some weird way. So we found that at least the sensors that we've looked at so far aren't very reliable. So we haven't used them a lot. If we found a better motion sensor and there was a better way to do this, then I think you're right. We could get much better results. Nest uses motion. So the Nest thermostat has a much better motion sensor built into it. But part of it is we're trying to use these like cheap little components, and apparently for the price that we've looked at so far, we haven't found anything better. Yeah.
So I know this is outside of your area since it delves into the psychology, but did you find that while measuring the electricity use in your house that you started to modify your own?
I'm about as guilty as the people I complained about in the first slide. For about 2 weeks, I was like, we shouldn't turn that on. Like, we walked around in the darkness, and I was like, let's combine both of these loads of laundry to the dryer so we only have to run the dryer once. And then after like 2 weeks, I was like, this is a pain. This is, So yes and no. And we've actually talked about that. I mean, there are some things I still do differently now that I realize, wow, that really is inefficient. But this is something in the Kellogg house, right? We've talked about how you would give feedback to a user, and what incentive do they have a user? I keep using this word user, occupants. What feedback do you need to give them, and what incentive do they have to actually react to that feedback? But I don't think I'm alone in that 2 week window. I think that's fairly common. You're willing to change for a little while, and then at some point you're like, whatever. But anyway.
Would it be just possible to just ask the occupants if they're leaving their house?
So
When you set up your alarm when leaving?
that was actually the intent of why I have these weird apps. You may be thinking, like, why did you spend time? So the Android app and the iOS app, the intent of both of those is to eventually have interaction. So you say, before you turn something off, you would just pop up on your iPhone, right? Your house, I just detected that you left. Is it okay if I turn off the coffee pot, right? So that there would be some remote control. And then you could imagine you could even build in the whole GPS thing. If your iPhone all of a sudden is getting closer to home, even though you didn't predict that you were going to be home for another 3 hours, you could imagine the feedback going the other way, right? Saying to your house, hey, yeah. And that's actually one problem we had, is that I don't go far enough from home to actually make the GPS, it would be very confused on a regular basis.
This is probably already answered, but since there's only a few ways in and out of your house, can you just do something with your doors when they open and shut, and assume that someone is coming and going when that happens?
If only, the challenge, there's a few challenges. If it was only occupancy we cared about, we would definitely have focused more. Like, occupancy was like one of the many things we were trying to do. The challenge is, as you know, I have a 3-year-old who may just open and shut doors randomly. Why not, right? Why wouldn't you do that? So opening and shutting a door doesn't necessarily mean I've left. So there'd have to be some other, the simple little mechanisms that we've used so far basically just say, it just gives you a binary, this was flipped. And so we'd have to somehow correlate that activity, that event, with something else to know for sure if we left. But we're looking into, if occupancy is the goal, I think there are other things we could do that might give us some more fine-grained data.
I was curious about the power requirements of the electronics you use to monitor your electricity.
Very minimal. Yeah, I mean, we've measured them, and I don't know the numbers offhand, but they're very minimal. Even that little plug, or the little computer, it's tiny. So it's a very, very small number. Yeah.
Have you looked into using open source hardware to monitor power usage, or do you really need like special?
The hardware you want to actually do. Well, so yes and no. We initially actually had, it was a winter study project actually, like way back when we were first starting this. We were using the TED devices, and we actually were hacking things to make them wireless. And so we were, literally soldering them, right? We were breaking things apart and soldering little antenna on them and things like that. But then we've tried really hard in the last few years to use just these off-the-shelf components, because anything that we have to do that's that custom is not going to help anyone else. And so, part of this is trying to come up with a system that is sort of cheap and can be replicated if people want to do it. But I do think that we could do some cool stuff if we wanted to, hack the hardware.
Just wondering if there's some, commercial versus residential.
Yeah.
Is there some low-hanging fruit there where you could kind of say, look, there's an awful lot of giant electricity users that are giant industrial things, where the predictability might be much easier, where because of, do you have any comments about that?
Yeah, and so a lot of this, when we focused on the home, and one of the things that moving forward, I don't know how well these devices scale. So taking what we did and moving it into a bigger building might be hard, but like you said, a commercial building. Exactly. And the funny thing is, there has been some work that was done in this area, and it was happening at UC San Diego when I was there, but it wasn't my project. The funny thing in San Diego is it's really hard to motivate it because you don't need heating or cooling. The temperature is like perfect year round. So, so they were doing all this stuff, and it's like, oh yeah, great, you've lowered it by a degree. I mean, it's like, but I think that a building that is a commercial building that actually sort of has this definite, everyone goes home by this time, that you might be able to instrument it with much fewer sensors and get even better accuracy, and the potential there is better. And I mean, even around here, right, you have the lights that automatically turn themselves off and things like that. So I think commercial buildings, it's a slightly different context that's easier in some ways, but harder in others because it is bigger. So a lot of these power line protocol things are gonna not scale very well.